Hello and welcome to Minute Learner AI. Today we will discuss an extension of the previous video. Uh, the last time I dealt with a simple linear regression example, but what if we consider a more real world scenario where we are trying to predict something based on several features, based on several independent variables. And I have one such problem here with me today. This is called the graduate admissions dataset. Originally built by UCLA, and what I'm going to use is downloaded from Kaggle. There is somebody who has published this gentleman here, 7 years ago, so way back in the past. I mentioned that I'll use the regression. In this case, it's going to be multiple linear regression. But again, if we concentrate on the framework, then we'll go in order, right? We'll discuss the business opportunity and then we'll quantify the expected outcomes and then look at the data and make a decision on what needs to be done. Here is the graduate admissions data set. Let's have a look at this. It's got data on graduate admissions for about, I think, 500 student entries. Okay, so we have these variables over here. If you don't count serial number, then we have 8. The whole explanation of these is given on this link that I opened. I will paste this URL in the description of this video. And yeah, I guess it'll be easier to access on YouTube. So the description of the dataset is given here. The parameters are GRE scores out of 340. So that's the maximum. TOEFL scores out of 120, university rating out of 5. So this is a ranking variable. Yeah, so it's going to be ordinal. Statement of purpose and letter of recommendation. So I'll go back to the Excel here. You see SOP. I'll zoom in a bit. You see SOP, this is statement of purpose, something the student or candidate usually writes and submits during admission. Letter of recommendation is something written by somebody else for the candidate. It could be a school teacher or a professor from the previous university. And then there is undergraduate GPA out of 10, which is the CGPA column in the data set. And research experience is 0 or 1. Either you have research experience or you don't, right? So that's what it is. And chances of admit means the probability that you will gain admission into this master's program, right? So this is also ranging from 0 to 1. Let's have a look at the values here. Normally, data is of several types. So let's have a look at the types of data since we are looking at a data set that uh, demonstrates almost all of them. Yeah. So nominal data is categorical data, no order or ranking. For example, uh, the variable called research in our data set, right? Has a student got a research paper published in their name or not? Yeah. So other data types, or sorry, other data examples that are nominal are gender, color, right? So you see, these are just categories. You can't numerically compare them with operations like greater than, less than, or you can't add or subtract them. You can't do that. So there are no mathematical operations you can perform on nominal data. I could say the same for ordinal data as well, except that a ranking is allowed, right? Ordinal data is categorical data, but there is ranking. So in our data set of the graduate admissions case, we have university rankings. So university ranking 1 is going to be up there on the top versus university ranking 2, 3, 4, and 5, going in that order. Yeah. So education level, for example, high school, bachelor's, master's, PhD. Yeah, this is also categorical data, but there is an order to it in the sense that you can say somebody with master's is more qualified than somebody with just a high school qualification, right? And somebody with the bachelor's is less qualified compared to somebody with a master's or someone with a PhD, yeah, a doctorate. So this is ordinal data. We have interval data now. Now you see the last two categories, interval and ratio, are considered to be continuous data, rather than categorical. Uh, Continuous data can be said to be measurements, right? So if you can measure something, you can quantify it, then that is continuous data. Um, I've written numeric data that may be continuous, like temperature, because you could go down as many decimal places as you want, right? Or pseudo continuous. Let's not be too fixated on the terminology here. I wrote pseudo continuous because something like integer values are still measurements. They are measurements, but we're not going into decimals. So it's just a term that I have written over here. Um, so, let's not fixate on that. But the difference between interval and ratio data is that interval data has no true zero. Yeah, like temperature, for example. Temperature could go down to, as cold as possible, right? Yes, the coldest temperature that has been stated to exist in our universe is 0 Kelvin. So if you take the temperature scale in Kelvin, yeah, you could argue that there is a true zero in Kelvin. But assuming that, that is the law that we all agree on today, the scientific community agrees that 0 Kelvin is the lowest possible temperature. I have written temperature in Celsius a as an interval variable. Ratio is simple continuous data. It could be temperature, let's say in Kelvin. Actually, no, this may be a very debatable topic. Temperature with units. So I'll just put weight. So age, height, weight, etc. could be ratio data. Yeah. Here's a question for you. What kind of data is your bank balance? Nominal, no. Ordinal, no. But is it interval or is it ratio? Does there exist a true zero or? Okay, that's something for you to think about. Let's go back to the data set. And okay, so easy to establish what kinds of data these are, right? The objective that we want to achieve is to predict the chances of admission of a student. Yeah. These are all probability values and they range from 0 to 1. Okay, these are probability values, but it is a set of continuous values. Yeah. This is also a ratio data. Okay. It's not categorical. If it were categorical, I would go for a classification algorithm. But for now, let's go with regression. And we'll start. There are several regression algorithms that exist. We'll see if multiple linear regression fits the bill. All right. Now, safe to say that as opposed to simple linear regression, that would be two-dimensional data, so it was easy to plot a graph. But to plot a graph with all of these, oh no, this is multi-dimensional data, right? Not even 3D. So it's going to be hard to visualize for us. We are just merely three-dimensional beings after all. So we are going to still use the same mathematical concepts to build our model, right? Now, a couple of prerequisites here are to see, let's go again and see over here. Yeah, for linear regression, linear relationship of data should exist. Now, as I said, we can't plot a graph for all of those dependent variables and independent variable combined, but we can do 2D graphs for some at a time. All right, so we'll draw some and see what they look like. Independence of errors is also necessary, equal variance of errors and normal distribution of errors. These are all different tests that need to be performed and go into the realm of data science. I would like to dedicate a different video for all of these kinds of tests, right? Looking at residuals, right? Looking at variance plots, and then for normal distribution, QQ plots and histograms, right? Um, those will be dealt with in a different video. For now, let's just assume that these tests are done and these prerequisites have been established, except that we'll just have a look at one or two graphs to establish linearity of the relationship. And we'll also see another important prerequisite, which is not written here, but it's about data transformation and manipulation, right? So it's more of a data prerequisite more than the model, and that is to do with ordinal and nominal data, right? So continuous data usually works well for regression models. Nominal and ordinal data needs to be looked at. Now, if we talk about research and university rating, research is binary data. It's nominal. It's 0 or 1. 1 is not necessarily better than 0. We haven't established that. That is not our judgment to make yet. That's for the model to do, right? And for the chances of admission to predict based on that. Cool. So normally with nominal variables, if as long as they're binary, it's okay to include them in regression. Yeah, your regression model, simple or multiple linear regression, is not going to perform terribly. University rating is the independent variable here, which is ordinal in nature. University ranked 1 is on top, and university rank 2 is next, 3, 4, and 5. However, there is no fixed interval between them. I will not say that, I cannot say that university ranked 1 is twice as good as university rank 2, you know, because then that is establishing a ratio. And this is not a ratio type of continuous variable, right? It's ordinal. And similarly, I will not say that university rank 2 compared to university ranked 4. 2 is not twice as good as the rank 4. It's just an order. There is no ratio comparison that can be done, right? So now this uh, this independent variable especially needs to be tested for linearity of relationship, and we are going to do that, right? Let's pick GRE score and university rating for testing linearity. If I make changes to the original file, it's not good practice, so I will simply leave it like that and create an Excel work. Yeah, graduate admissions predictor, right? And I'm going to pull the data from the CSV. So I'm going to create a copy over here. How do I do that? I go to data, And Excel has this from text slash CSV option. So the dialog that opens is, God, I have to do this all the time. Yeah. So this is the file that we are going to query. So now Excel is making a connection to that CSV file. You saw that little dialog here, and it's going to query the data. There, this little dialog shows us just sample of 20 records of that along with the headers, right? Delimiter comma because it's a comma separated value file, and we don't need to transform data. Everything is fine. I'm just going to load it here. Okay, so we have this. Uh, Another thing to note is that data transformation is something we didn't need to do. Usually, Kaggle datasets are cleaned up data, and you don't have to do all of that. But let's say if the university rating wasn't in numbers 1, 2, 3, 4, 5, and instead it was first, second, third, fourth, fifth in words, string values. You may want to convert those into numerical values over here for linear regression to work and perform optimally. Right. So we have this data in Excel now, right? It's not the original data, it's a copy of that. So we are going to work on this. Now, I want to establish linearity of data. So what I'll do is I'm going to select, let's say, GRE score. I'll hold down control on my keyboard and click chance of admit. And I will insert a chart. Yeah, I think the just scatter chart is fine, right? Yeah, so this is my first chart. Let me make it a little smaller so it fits in the screen. And you can see that on the, yeah, I think we need the access titles. So you see, compared to the GRE score, the plot is, I think, more or less linear. So we can work with this. It's not bad. I'm I'm manually drawing a line over here. It's gonna be something like this. It more or less follows the line. Also, you can see the spread of the data points is not too big across different sections of the chart. Yeah, it's not too big. The spread of the data points. It's not like they're very widely spread at the bottom. There's a little bit of spread, but it's not that bad. Let's do the same for university rating as well. I'm going to select university rating and chance of admit. Go to insert, recommended charts. Yeah, I think the scatter chart is fine. Uh, Naturally, the university ranks are not 0 and 6, so there are no values over here. It's going to be from 1 to 5. That's why the dots are all over here, right? Also, university ranking is ordinal data, it's not continuous. There are no ranks like 1.5 or 2.5 or 3.6. So obviously there are no values in between. All of the data points here, if I were to draw a line through the approximate uh, means of each distribution of dots for each rank, those are going to be close to this line. It's uh, actually going to be all right, you know. So also the spread of each of the points is not varying too much along the range. So, I think we are good to go. You can test for linearity visually like this for each of the independent variables versus the dependent variable, and you're going to be fine, right? So, I think let's just go ahead with this and build the model. But before that, the rule is split into training and test datasets, and that is what we are going to do with the Excel random function. All right, here we go. Randomizer equals the random function, and we get a set of values. Excel random function has a bad behavior of changing these values every time you try to do any little thing on this data set, on this entire workbook. Like, see, I type something in any other cell, everything goes for a toss. I delete these values, the randomizer values change again, right? So the same way that I did for the simple linear regression example, I'm going to copy all of these values, right? And as you can see, the random function is being shown in the formula bar for each of these. I'm just going to paste over this data, the values, right? Paste values. There, the values have been pasted and the random function is gone. Now these values are set. They are not going to change. So good for me. I'm going to sort smallest to largest. There are a total of 500 values. Let's go to the bottom. You can see it's still row 501, right? So there are a total of 500 values. I'm going to use, I'm going to do 70-30 split, right? So 70% of 500 is going to be 350, and that's going to be my training data. Whereas the rest of the 150 are going to be test data. So let me create my training and test data sets. Okay, on training, like I said, I'm going to go to 70%. So 350. Until here is my training data. So after this one, I'm going to delete everything. And that's it. For the test data set, starting 352, everything is good. I want to keep it. So now I have 150 rows for test data, and for training data, I have 350. Going to look better if I sort by serial number again, even though serial number is not going to be in our model at all. Okay, it gives us no information. It has no influence on the chances of admission. Serial number is going to be excluded from everything. Now let's have a look at all of these. Okay, I think data is set. All we have to do is open Excel Miner toolpack. We are going to run linear regression. Yep. Input y range is going to be column I, except not I2. I wanted to go from I1. And input x range is going to be the rest of the range. There you go. Labels are included. Constant is 0. No need to check this. Confidence level 95%. If you want more coverage of data, but precision is not that much of a big deal for you, then you could set the confidence to 99% as well. Yeah. For now, 95 is good for most cases, so I'm going to keep it at that. My output range, let's just put it right next to it. I do want the residuals. Yeah. I want the line fit plots. Let's also include the normal probability plots at this time, so that either in this video or the next, we can use these for a further explanation of the data and the results that we get. I'm going to click on OK, and I get my summary output. Let's close the toolpack and have a look at what we have. Now, the thing is that let's start from the top, regression statistics, right? A few questions that everybody should ask is one, this regression model that we generated, how well does it fit the training data? You know, um, is it really fitting it, and is it going to be a good predictor or not? Right? In fact, it's not that simple a question. It's not a yes or no question. It's how good a fit is it, right? By what percentage, for example. So there are multiple ways to do it. Though I have shown this before in a previous video. Let me go back to the how to interpret linear regression. Uh, when you have to understand the fit of a simple linear regression model, the R squared value does the job pretty fine, right? However, the adjusted R squared value is going to give you the same information but better for multiple linear regression. It's the R square adjusted for the number of predictors, because as opposed to simple linear regression, we have many independent variables in multiple linear regression. Since you have many predictors, you have many more degrees of freedom, and your data is going to have a lot of points over a multidimensional plane that is trying to predict the dependent variable, right? In our case, it's the chances of admission. So, the more the number of data points and the higher the complexity of data and the model, the greater is the chance of overfitting. Adjusted R squared value actually penalizes some unnecessary variables to avoid overfitting, right? So, the R squared value may not be able to do that. Um, the coefficients and intercept are going to be used to construct the multiple linear regression equation. I will demonstrate that in a bit. And the p-value tells us whether a coefficient is statistically significant. Means is that predictor actually influential for the dependent variable for what you're trying to predict, right? If it's not, the p-value will tell you that, and you can just exclude that feature from your linear regression. Significance f is overall p-value for the regression model. Tests if at least one predictor is significantly related to the response. In simple linear regression, this would not really help you much. But in multiple linear regression, yeah, you have several predictors. So, you do want to know if at least one of them is actually uh, effective on the if it's effectively predicting the dependent variable. So, that's why it's important. So, that's it. Let's just go back to our Excel and have a look at these again. Okay, so adjusted R square is 0.829, so almost 0.83. It's good. It's not bad, yeah. In the ANOVA, F value and significance F over here, right? So these are also going to be useful now for our case. So significance F value is fairly small. Is it actually zero, or are there any wrong button? 0.00. Okay, not bad. The significance F being zero means that this entire model is statistically significant. Yes, at least one predictor or more are going to be are statistically significant for the dependent variable named chances of admit, which is the chance of admission. So that's good, not bad. We have the coefficients of all of these features, and I'm going to highlight this. And let's have a look at the p-value as well. I'm going to highlight this, right? So now these are what we are going to look at for evaluating our model. right? From the top, we've seen model fit is good, significance F value is good, is great actually. So good. Next, coefficients are here. These are going to be used to construct the prediction model, but let's have a look at p-value. Now again, the p-value has to be equal or less than 0.05. And if it is within that range, then the corresponding predictor is statistically significant, right? So, this p-value is actually for each predictor. Let's go from the top, the intercept to the bias. Okay, it's a very small value. It's like exponent minus 24. So there are at least 23 zeros after the decimal point. GRE score, yes, it's way below, it's very small, the p-value, way below 0.05. So we are going to keep this. So that's the decision we make, right? According to the p-value. Do we keep this as a predictor or not? GRE score is good. TOEFL score also very small. Okay. Way below 0.05. We'll keep it. So university rating is quite large. It's above 0.05. So, this is not statistically significant as a predictor for chances of admission. That's something to be noted. Now, the statement of purpose also the same. It's 0.56. It's way above 0.05. And, it means that SOP is also actually not that significant for predicting chances of admission. Whereas the letter of recommendation, okay, this seems to be significant as a predictor. So we are going to keep this. I think I'll just highlight them separately. Yeah, I'll highlight them differently because the p-values are small. Letter of recommendation is good. CGPA also very low p-value, so it's a good predictor. And research. Who knew? This variable is also statistically significant. Even if the p-value for these university rating and SOP, if they were like, 0.07, 0.06, close to that threshold of 0.05, I'd still consider keeping them. But, they are way off. They're way off that threshold. So I think it's best to construct a multiple linear regression model without these, right? So I'm going to exclude these from my training data altogether and not have them at all. Good. Let's run this again. But before that, actually, we generated some plots over here. And maybe it's a good idea to have a look at them one by one. This chart does not really show it right now, but there are blue dots as well. They are just hidden behind the orange dots. So these plots are great for assessing the quality of the prediction, right? With chance of admission and predicted, uh, it's hard to judge, but it's hard to judge for each point. But at least if you look at them as a group, they're all within an equivalent range, so they're not too far off. Even if I look at the combined uh, mean squared values or mean squared values of the population for predictions versus actuals, they would be in the same range. So I think it's good. We are good here. Let's have a look at the others. The actual values are in orange. Predictions are in blue. Naturally, it's multiple linear regression, so the predictions would be more linear. I mean, that's the model. That's the nature of the model. Just on a two-dimensional plot basis, just looking at CGPA and chances of admission, actual data does not have linearity. So here I think we are a little off. Yeah. But again, uh, if we talk about the prerequisites for choosing linear regression, it is that the data should also be arranged in a linear fashion, right? The problem is that we are trying to look at just one independent and one dependent variable and saying that it doesn't look linear, but on a multidimensional plane, combined with all of these variables, all eight of them, maybe there is some linearity, so it's hard to visualize, but there are actually certain statistical tests that can be run on such data to establish linearity or non-linearity of the relationship. So that will be content for some other video. Anyway, this is good. LOR line fit plot also looks fine. I think for values that are 1.5, our predictions might be a little off compared to the actuals, but that's just how it is. Okay, so that's for letter recommendation. And yeah, so I think I think I'll not waste time going through each of them. Just try it out yourself and have a look at all of these plots, analyze them, and see how the predictions versus the actuals are arranged for each independent variable. I'll create a copy of the training data. I will delete all of the previous results that I got. Okay, because we want to run multiple linear regression without two of these predictors. Its university rating and SOP as established earlier. So uh, hiding columns is not going to work on Excel. I've tried it before. Trust me. Deleting actually works. Now what I'm going to do is I'm going to open Examiner toolpack, quickly do the same thing. Again, Y range is this, and X range is going to be, just like to select it from the bottom, and all of these are selected except for serial number. Good. Uh, I'll have the residuals, and I think for now it's okay. I'll just do this much. Oh yeah, output will be here. And yeah, it's done. We have the output again. Regression statistics are here. I just like to usually box them all in so that it's easy to have a look. Right. So once again, adjusted R square value is what we use to evaluate the model, right? So I will highlight this. F and significance F values. So the F value is like the P value, but while the P value is going to give significance of each predictor, F value gives the same thing for the entire model. Yeah, so that's what it is. It's a fairly large value, so there is no benchmark here for F value, but it's way above 1, so it's fine. Coefficients are going to be these. We're going to build the model based on these. P-values, again, I'm going to highlight. Let's have a look. So let's start from the top. Adjusted R square is 0.83. Have a look here. What happened after we removed two values? Let's go to the training data set. Adjusted R square was 0.8299 earlier. Now it is 0.83. It's a very minor change, but it has improved from last time by removing SOP and university ranking features for training. So this tells us that the model is actually fitting the training data better. Very marginally, but yes, there is an improvement. Significance F is still 0. No need to talk more on this. We all know why. P values for the intercept, great, very small. GRE score, yeah, way below 0.05. TOEFL score also very small value. LOR, CGPA, research, we're good. Everything, all the p values here are way below the threshold of 0.05. So our model is good. Now let's construct the multiple linear regression equation based on all of these. Yeah. So what I'm going to do is the residuals are here. So I think I'll construct it somewhere here. This is not an Excel formula I'm writing. It's just text. This is just a representation of the mathematical equation. right? So becomes generally like m n into x n. So now you see x1, x2, x3 are all of these, you know. So GRE score, TOEFL score, LOR. So it's x1, x2, x3, x4. These are the independent variables, and m1, m2, m3, m4, etc. are the corresponding coefficients that we have just calculated using the multiple linear regression feature of Excel Miner tool pack. So we are going to construct this equation. The last thing over here is m naught, which is the intercept, which is equal to this value, right? So that's all it is. Uh, Now, if I say CGPA and research, and I have the intercept. If somebody has a GRE score, okay, 324, TOEFL score of 105, letter of recommendation is 3, CGPA is 8.4, and research no, right? Intercept will be, well, whatever. So now I have to construct. So these are my x1, x2, x3, all of these values, right? This is just going to be this, right? Until x naught, and coefficient multipliers are over here. Okay. So I'm going to write the formula here. Now this is an Excel formula that I am writing actually. So it will be this multiplied by the corresponding coefficient. Okay. Plus this for the actual x values. I just anchored the column in case I want to write more. Okay, so we have this result over here where for these values the chances of admission is going to be 0.68. So this is the prediction model that we have just constructed. Congratulations. And this is the equation that we're going to use in the test data also to predict the values based on our model. And then we are going to compare to the actual values in the test data to see the accuracy of the model. Now in regression, there isn't a formal concept of accuracy, but we are going to use the method of comparing the differences in actual versus predicted values using the modulus of the difference or the average mean squared errors across the entire data set. With this, I'm going to go to the test data, and this stuff here, this is my actual model. So I'm going to just copy the stuff here. Only the values are here. Good. Right. So again, just so that we remember, I'm going to paste this multiple linear regression line over here. Let me see. Yeah, predictions. Okay, so this is what I'm going to put here as predictions. Now I have to put that same formula here again, and it's going to be a pain. So I'm going to do this, and I'll just cut the video to the part where I've written the entire formula. And there you have it. This is the entire formula. The coefficients multiplied by the corresponding value in the test data set. And yeah, these are the predictions we have. So fairly close to the actual values. So I think a model might be fine. But again, we shouldn't really say this without really performing the test of accuracy, right? The average distances or the average mean squared errors. So let's do that. Yeah. Let's evaluate how good our model is performing on the test dataset. For that purpose, I'm going to insert a few columns here to perform that calculation. All we have to do is squared errors, right? So SE squared errors is going to be equal to prediction minus actuals to the power 2. Actually, let's have more significant digits and we'll know what's actually going on behind the scenes. What I've done is I've taken the difference between actuals and predicted and I have squared them. Why did I square them? Because the difference might be positive or negative. I just want the difference, the absolute difference. So I squared the value. The next thing is if I want to get the mean sum of squared errors, then I'm going to do the squared errors. Next, I'm going to add all of them and divide them by the number of these uh, test data values. And then at the end, if I do a square root, then yeah, that's going to give me a value that can be used for assessing how well the model fits. I don't want sum of squared errors as a part of the table because it's going to be sum of this entire column. Okay, so the mean squared error is going to be I'll just divide this by the total number of data points, you know. Yep. So, if you want to just stop here uh, and use this value to evaluate the fit of the model, that's quite okay. Normally, I like to compare it to, the actual value. See, this is a set of squared values of the errors. Sum of squared errors is also still a squared value. Mean squared error is also still a squared value, right? So there is no benchmark for how good a model is based on the MSE. It's not like the p-value, which has a generally agreed benchmark of 0.05. It's not like that. So to compare, I need a value that is equivalent to compare to the predictions. So what I'm going to do is root of mean squared error, and it's going to be square root of this, right? So now I have a value to compare to the predictions and the chances of admission, right? So generally, um, I want to compare to, let's say, mean of chance of admit and let's say mean of predictions, right? I think these would be fairly okay. Where is average? Yeah, arithmetic mean is fine. Average of this is good, and average of predictions is good. Okay, great. So generally, this is the absolute average, yeah, just the normal arithmetic mean of chances of admission and the predictions, right? What is the predicted value? So compared to this, the root mean square error is a very small value. If I have to make a comparative value to this, then let's say equals this divided by this. Yeah. So if I just put this and copy this value here, and there we go. Right. So the root mean square error is just 9.33% of the average value of chances of admission and 9.28%. So you see, the error is less than 10% on average. Like that's the simplest way that I could define it in layman terms, right? So if it's that small, if on average your prediction is not going to vary by more than 10%, then yeah, I think that's good. The model has actually fit the test data very well. So therefore I think apart from the one tweaking that we did in the model, which is university rating SOP that we removed, right, to increase the average adjusted aspect value, I think that's good. Thanks for watching and stay tuned for more videos to come.